So now let's look at how the routing happens in the NDN. So NDN routing operation is actually uses the name based routing, that is consistent with the ICN philosophy, and the routers themselves maintain three different data structures or the elements inside them. So one is called as the forwarding information base. So this is exactly similar to that of the routing table. So whatever is the IP address table is there and the forwarding table is there. So that is the forwarding information base in the TCP/IP network. Similarly, the named tables are there inside the NDN architecture. That is one piece of information. So that will help you from where to get the content from. So in the TCP/IP communication, given a destination IP address, I am finding one IP address is given on which port number I want to pass on this, and what is there in the NDN architecture is given a name, let us say ABC, and where to go to get that content. So IP address are simply replaced with the names that is it, including the prefix. So here in this case example that I took, there is no prefix, but it can be a prefix name. So that is the difference. This is called FIB information. And then the second component is something called as the pending interest table. So whenever an interest packet comes to a router, and there are two operations that happens. One is you consult what name chunk that it is requesting for, and check whether the content that is requested or the named content that is requested is there inside the cache of your own cache, and if it is available, and you supply this, and if it is not available, you forward this request interest packet to the next hop router along the path to the where the content is available. So while this is getting forwarded, the interest packet gets forwarded, it remembers the I have forwarded a request for the content so and so, maybe the content ABC, and it is pending. So whenever the response comes, then who actually made that request, against whose request I sent this interest packet in the first place, and then when the data packet comes from the other end, you match it and then you forward it to that particular host in the reverse direction. So this mapping is done using the pending interest table, and in the process, whenever the new content is actually received by this router, it may decide to cache the content. So if the space is available, it can cache it. It can, if the space is not available, still it can cache it by replacing some of the existing content. And if the you can also base the decision to cache the content or not to cache the content based on how popular the content is. I can use some notion of the popularity. So whether this content has been used in the past or not, based on that I can decide to cache the content or not to cache the content. So these are the possible things. So you have a forwarding information base which is as similar to that of a routing table, which will tell you where to get the content, and the pending interest table will have the information who has requested for the data in the first place, and when the data comes from the other end to whom it has to be forwarded, that information is kept in the pending interest table, and the content store simply has the cached content in this particular place. So this is how the request reply movement actually looks like in the NDN architecture. So the interest packet, as I said, is flowing from the requester node to the data source. So this data source may be the original data source, or a node or a replica node, or a router which is having the content, And in the reverse direction, the data itself is having three things. One is the name that is requested in the interest packet, and the content itself, and then the signature, and this actually flow in the reverse direction. So you can think of this communication is the symmetric in nature, in the sense that symmetric in the sense that if I take the same route, so let's say here is the recipient, and these are the three routers, and here is the sender, and if there is an alternative path available from this sender to the in the IP model, what can happen is the packet number 1 can take this route, and through these set of the routers the packet can reach the receiver. The packet number 2 key is independent of the packet 1, and it can flow through the second direction. So this can happen. Every packet is carrying an IP address, and they independently flow in the network, and they reach the intended recipient. But unlike that, the Indian communication is symmetric in nature on per request basis, meaning wherever the request through which interface, through which sequence of the routers the interest packet has gone, in the reverse direction through the same sequence of the visiting same sequence of the routers, the content is actually delivered to the intended recipient. So if the path taken in the forward direction and the path taken in the reverse direction are just opposite to each other, this communication is called as the symmetric communication. And the Indian mostly follow the symmetric communication paradigm. But in the IP and HTTP IP network, we might have the asymmetric communication as well. So although on a larger basis, majority of the routes might take still the symmetric sequence of the paths, but occasionally you might have some packets taking a different route. This might be simply for the load balancing purpose, or any other purpose, or any other reason. But the Indian communication also, different requests can take the different routes, but on a per request basis it is going to be symmetric. Wherever the request has gone, the one data chunk as a reply to that is actually coming in the exactly the opposite direction. So this is how the routing and the three things, PIT, content store, and the FIB information in the Indian architecture look like. So what you have, every router maintains all three of them, and there are two producers here, data producer. This is the publisher number 1, second one is the publisher number 2, and here is the client which is actually making the request, which wants some content to be delivered to it. So as usual, the client is the one, because Indian is a receiver driven architecture, the client is the one which initiates the communication to get some content, and it sends a request. The sequence, the packet number 1 is an interest packet going from the client to the first hop router, and when this request comes, so the router number 1, here in this case CRA, is the one which looks at its own forwarding information base and then its own content store. First is whether this content is available in my content store. So at this point of time, so this is the structure of all the three entities. This is from here to here is the FIB, from here to here is the PIT, and from here to here is the content store. So when the interest packet arrives at this router, it looks that here in the content store there is nothing there, so it is blank. So that means that the content is not there in its local, it cannot serve, and then it looks at its own FIB information. So assuming the content queried is for something which is having a prefix aueb.gr. So it looks upon which of the next hop that I need to forward this interest packet to, and it says that you need to, the FIB entry says that you need to forward it to the CRC, that is content store number C, and this particular router. So it forward that request. At the same time, it actually logs that request, the details, into its own PIT table. So this is the exact content that is asked for, aueb.gr/ci/new.html. So that is actually produced by this producer. So there is one client which has asked for so and so content, and the FIB information said that I need to send it to the next of this particular router, and then send it to that router. It sent and then created one entry. And again, the next hop router, this router will also do a checkup. It also looks at its own content store. Here is the, after receiving the request, it looks at this content store is empty. It also doesn't have the content, and then it creates its own one entry in the PIT and looks at the FIB where it has to forward. So it says that anything that is having the prefix aueb.gr, you should forward it to publisher number 1, which is actually giving you the data. You get the you make an entry in the PIT, send it, and then you get the data. So publisher is the one which gives you the data. This dotted lines on the with the green color lines, it will indicate the data in the reverse direction. Once the data comes to this router, and it's again checks, okay, this is the content name having so and so prefix, and I have a PIT entry already with that particular name, and who actually queried it, I need to send it to the CRA. From which router I got it, this router I got it, I need to send it to him, and he erases this router, erases the entry, PIT entry, after forwarding after the content is received from the publisher, and then it will forward it to this router and erases the PIT entry because the content has been already delivered. In the process, it can cache the content and update. Okay, the same content which I am forwarding now is also available in my cache, so it is stored, and then it is forwarding the content. And now once this router also receives that content, it will also look its own PIT table, which is looking like this, and it erases the PIT entry, and it might also decide to cache the content and create an entry in its cache store. And finally, after caching this content, this might CRA might deliver the content to the subscriber. So this is how actually it is going to operate. So in summary, FIB information will tell you which is the next hop where you have to forward the packet to interest packet to get the content, and then the PIT table tells you who has made the request and whose request is yet to be served. Only those entries are there in the PIT table, and content store is actually having the names of all the contents and also the content, the data itself in its memory. So that is what the structure is. So and again the next hop information is found out by using a longest prefix matching mechanism. So here in this case, so the content that is requested is aueb.gr/ai/new.html, but there is also one more entry with aueb.gr/cs. So that is a different prefix. So if anything having the aueb.gr only gr matching with only this one, then you need to forward it to C. Otherwise, you need to forward it to B. That is what these two entries actually indicate. So just like the IP prefixes are the longest prefix matches, here also it is the name, the longest prefix match using the names. So that is what the Indian routing architecture would look like. So what the routers actually have, and to keep updating the information. So this kind of the name based routing mechanism of the NDN, or in general any ICN architecture, actually helps in many ways. So here are few of the prominent ones. It also because the names can be of arbitrarily sized, and it helps us to get rid of the or address the problem of the address space exhaustion. We all know IPv4 addresses are limited in number, and we have reached the we have exhausted all the IPv4 addresses almost, and now IP version 6 came, and there is no guarantee that IPv6 also sometimes at least if not now 50 years down the line or 100 years down the line, it might be exhausted. So then how do I deal with that? So if you have an arbitrarily sized name, and then that problem is solved. I no longer have a fixed sized addresses or fixed sized names. So any name I can give, so that problem can be inherently addressed in the NDN architecture. And because of the IP addresses restriction, scarcity of the IP address availability, we came up with this NATing technique, where the public IP address is mapped to a private IP address to establish the communication between a device which is behind a NAT firewall with an outside device. So that is also not required here, because every entity is independently named, everybody is querying with an independent name. There is no need for having the NAT traversal. So in effect, these two things will make the address management much more simpler. Address management here in this case is the name management. And unlike the TCP/IP model, where IP uses a stateless communication mechanism, so here in this case the routers are becoming stateful, because it is they are keeping the entries in the PIT table. So if two different how does it help is, if two different clients C1 and C2 request for the same content, let's say A/B/1, and he also let for A/B/1. So if the C1 is the first one which has queried for A/B/1, and subsequently C2 queries, so the router notices that there is one entry in the PIT, its own PIT table with the same name A/B/1, and it has been forwarded, it has been requested by the C1, and now there is no point in sending the second request from the C2 to the same data producer or the next hop router. So what it does is content C, whatever the content that is A/B/1 is requested by the client C1, and now when the second request comes, it will add an entry with the name C2. When A/B/1 comes back from the other end, I need to deliver it to both C1 and C2. That is what it actually means. So if there is already a pending interest table entry for a particular named chunk, and the new client or the new subscriber makes the request for the same content, then the request interest packet is not forwarded to the next hop. Instead of that, it is dropped there itself, but a PIT entry with a name with the previous hop information, here in this case the subscriber, is added to the PIT table. So this is happening both, even if it is the next the requester is not the client but our subscriber, but a different router, then also the same mechanism would work. So for example, if I have two different routers, the client C1 is connected to the first one and the client C2 is connected to this one, and if the PIT entry is both of them, assuming C1 and C2 request for the same entry, the same content A/B/1, and assuming C1 request first and then it is already there, and this router is already sent that interest packet to the next hop, and through this intermediate router, the C2's request will also reach this router. Then also it will just create an entry with the name C2. Here in this case, if you name these routers as R1, R2, R3, So this should be R1, this should be R2. So I need to send it to the router number R1 and also to router number R2. That's what it means. So that is how the PIT table is actually maintained, and it will help minimize the number of the interest or request going to the content serving node. So we are not finding, unlike the in the IP model, what was happening. So if multiple client requests, so all of them, they are independently getting the content multiple times. The content is getting that is actually minimized here in this case in the Indian architecture. So often the content, because the content is stored in many different places inside the network, a same content might be available at two different routers, and a particular router, when it is forwarding the request to one particular data chunk, so it can still do the load balancing, you, in the sense that sometimes I send to the router number, if let's say router number 1 and 2 have the same content, and if the same content is some content is requested which is available at both places, sometimes I might send it to the router number 1 and sometimes I might send it to the router number 2, and you can still do the load balancing. That is still possible inside the Indian architecture as well. And of course, if you forward the request in one direction, if the connection fails, then if multiple other sources also have got the same content, then you actually, then you try. First you try one path. If you don't get the content, then you can go and check in the, or explore the alternative paths as well. So that is possible inside the Indian architecture. So there are some mechanism to also handle the inherent the problems that are available in the TCP/IP communication, which is the congestion. So because of the congestion also, the routers might decide to not to send the interest packet in a particular direction, but it can actually send it an alternative path, or it might may not be able to handle the interest request because of some other reason. So let's say I have a router here and the interest packet is coming from some source or some other router to this particular router, and if there is a congestion, assuming this is the only path, next stop path from where I can get that content. Let's say take the same example, A/B/1, and this is the only interface on which I can send it, and if I know that this particular router and this link is heavily utilized and it is congested, and this request that is coming from the other particular router or the client may be dropped right here without creating an entry. PIT entry is created only when the request interest packet is actually forwarded to the next hop. So if you are not forwarding the interest packet, then there is no PIT entry in the table. Or in some other scenarios for security reasons. So in the previous lectures also we discussed, one is somebody can generate too many number of the named content and try to publish in the network, overwhelm the network. The other one is somebody can maliciously keep sending the request to a particular router. I want A/B/1, I want A/B/2, I want A/B/3, something like that. Or to the same named content, many different requests are sent, so that this guy actually spends a lot of time in servicing those requests. That is the case of the denial of service. So if the router learns that a particular request coming from a particular source or a particular port number are actually malicious set up the request, they are intended to kill the or burden the router itself, then it might drop the request without forwarding it to the next hop. So whenever it drops the content, it might also tell in the reverse direction, the requested content is not available with me. You can try elsewhere, or it is not possible to serve the your request at this point of time. So if you use this kind of the load balancing or the selective forwarding mechanism for whatever the reasons that I just mentioned, so that will help you to manage the PIT table entries. So remember, assume this case, if you don't discard the internet packets, if some malicious guy is sending the too many number of the requests without any purpose, then the PIT entries, because he is asking for so many number of the data chunks, so you keep on sending the next stop, they may not even be available. So then your PIT number of the entries in the PIT table would go substantially. So that is not desirable. So you may not be able to accommodate the new genuine request coming from some other sources. So another way of dealing with, one way is you drop it without, don't create the entries in the PIT table, or you send the negative acknowledgement saying that so and so content is not available, or you put another way of dealing with that is you put a timer for every PIT entry. So A/B/C is requested by client 1, and the time for this one is, let's say, 1 minute. So within 1 minute, I should get the content from the other end. So to whom I sent a request, from that guy, I need to get back the content within 1 minute. If it is not coming within 1 minute, then you purge the entries in the from your PIT table. So this will help you to keep the PIT table at a manageable level. Otherwise, the number of the entries will grow substantially, and that will become a burden for the operation. So that is about the routing and the forwarding. And the next feature of the in architecture is the caching. How does the caching actually happens in the NDN networks? So caching, as usual, help reuse the data, and it will also help you to serve the content quickly, thereby reducing the latency of the transmission. So that can only happen if you make the routers content aware. So meaning what request being what kind of the content is being requested by which client, and what is available in their content store. And this caching work without the notion of the port numbers, and there is no danger of the congestion collapse, and congestion control mechanisms are not required, because I am no longer establishing a connection between the two parties. It is just I send one request, against that some data would pop up at my door. So with using that simple mechanism of forwarding the request and response, so the NDN proposes to use a very simple caching technique, which is something called as the leave copy everywhere. What it means is, if the requester is here or the receiver is here and the sender is here, and the intermediate routers are these many, so if some data comes, if let's say the data is D1, so D1 is available in the content store of this router, maybe the R3, and D1 will be stored in the content store of the R2, so D1, and the D1 would be stored at the content store of the R1 as well. So wherever through what all the routers the content is moving, in all of those routers content store, you put this copy of the D1. So that is called as the leave copy everywhere. Wherever you visit, you just leave a copy there and then move. So D1 came here, it left a copy of the cache of the R3 and then moved towards the R2, and then it left a copy there and then it moved to the next stop, and so forth. So this is the one of the simplest caching mechanism that you can use, but there are other caching techniques as well. So this one is the basic caching techniques, but the other techniques which actually maximize the utilization, a simple technique might be, I need not cache it on all the routers, but only on the router which is directly connected to the client. So this is called as the edge caching mechanism. So edge caching means that I cache the content only on the in the content store of that router to who is the requester or the client itself is connected to. So that is called caching. So this is another caching mechanism. There are many other different caching mechanisms that are developed over a period of time. But the default and the simplest one is this leave copy everywhere mechanism, which actually stores a copy of the content D1 in every router's cache. So that's about the caching, and the security in the NDN is in line with the security of the required in the ICN network. So we provide the security to the data chunks itself. So how does that operate? You take the content, and the content itself is actually digitally signed by the producer. So the requester is here and the producer is here. Producer produce some content, let's say D1. So you take the D1, pass it on to some algorithm, hash based algorithm. You get a signature. This will use a key. Whatever the signature that is generated, you attach to this, and then you transmit this to the internet recipient through some series of the intermediate routers. So this is how any piece of the data you take that, and then you attach a signature using a key signature generation algorithm, which is actually basically a hashing algorithm which uses a key, and then you transmit it over the network toward the reducer. So this chunk is along with the signature is actually going through this series of routers and then finally reaches the recipient. So that is how the security in the NDN networks actually work. You basically sign the data chunks using a cryptographic algorithm. So that brings us to the question, how does the receiver actually verify the content? So you need to know in order to verify the received content, you need to know the key that is used to sign the data. So assuming there is an offline mechanism to share the key with your recipient, then the recipient will be able to verify the content. So there are again different ways of delivering the keys or sharing the keys to the intended recipient. So remember earlier discussion, we said that not all content can be shared with everybody. So we want to put some kind of the restriction. A selected set of the people would be only be able to view or access the content. So that's the access control mechanism, and we can actually control that as well. So if we have a key distribution mechanism, offline mechanism, or some other way of through the NDN medium itself, we are able to deliver the keys to the internet recipient. Only they can actually verify that signature and read the content and then make sense of that content. Otherwise it's not possible. Through this mechanism I can actually enforce the access control for the data that is generated by some data source. And this kind of the mechanism, the security, providing security to the data chunk itself has got many advantages. So many of the cyber attacks that are possible in the IP networks are not exactly applicable in the NDN network. So for example, I cannot actually bombard a particular recipient with too many number of the packets, because the routers themselves do not forward anything unless somebody has requested something from the. Let me summarize what we discussed. So NDN is a clean state design. So it operates using the names. The data chunks are named. Hierarchical naming convention is preferred, and the flat naming convention is possible. And the namespace itself is not controlled by the or dictated by the NDN architecture. So you can use, as long as you use the any of the supported naming convention, you can use any possible name of any length in the NDN architecture. And the routing itself happens through use of the three elements inside the router. One is the FIB store, second one is the PIT table, and the third one is the content store. and the FIB serves to helps you to find out from where to get the content. PIT table tells you whom to forward the data that is received, and the content store will keep the copy of the content. And the caching mechanism in the NDN is a default mechanism, very simple, which is the leave copy everywhere. All the routers which receive the content will store a copy in their caches, and the security in the NDN is given through by cryptographically signing the data chunk that is generated, and which the receiver can actually verify subsequently. So that is the big picture of the NDN network. We'll stop it here. We'll come back and discuss the few other architectures in the ICN paradigm.